So hello again. Welcome to lecture 17 on series. We're going to talk about absolute and conditional convergence here. This is going to be a pretty short lecture, but I want to get into the definitions of absolute and conditional convergence, and then we'll look at the ratio and root tests to test for it later on another series lecture. Last lecture we talked about alternating series. That was the first sort of test we got to work with series that weren't all positive. Now, series that have all negative terms, you can just factor out a negative and look at what's left and then see if that converges and multiply by that negative. So all negative terms work like all positive terms. Alternating series, of course, you just use the alternating series test. But, you might have some other series that do other weird things. I mean, series are not set in stone. They may have lots of negatives and lots of positives or some other weird things. So I want to just point out a series. So let's define these things. So a series in general is said to converge absolutely if the series whose terms are the absolute values of the entries converges. It says to converge conditionally if it converges, but not absolutely. Now, we'll make an argument later to show that if it converges absolutely, it converges as well. So absolute convergence is stronger than regular convergence in general, unless it's a series with all positive terms, in which case it's the same thing. But let's look at this series. Of course, this one we've seen before, right? This is the alternating harmonic series. Let's start with n equals 1. So we have -1 plus 1/2 minus 1/3 and so on down the road, right? And we saw in another video that this converges. However, the series consisting of its absolute values, -1 to the n over n, well, that series is just the harmonic series, and this diverges. So this converges conditionally, not absolutely. The series of its absolute values does not converge, so it converges conditionally. Whereas if I look at this one, this is another alternating series, minus, let's start from 1 again, so it's -1 plus 1/4 minus 1/9 plus so on. It's an alternating series. The terms go to 0, so it definitely converges by the alternating series test. And if I look at this over here, the absolute values of these, -1 to the n over n squared, know that some of the absolute values is going to be this p series, right, where p is equal to 2. So this converges. So it converges. And so this converges, but also the series consisting of whose terms are the absolute values of these terms also converges. So this converges absolutely. Okay, and let's look at this last one. Well, look at that. This last one is, in fact, a series with positive terms. So that happens to equal the series, the absolute convergence series, right? And since that converges, since this first one does converge, since it's a geometric series with r equal to 1/2, so this thing converges absolutely. If a series with positive terms converges, it converges absolutely. In fact, you can check if a series with all negative terms converges, it also converges absolutely, because you just factor out the -1 and you have a series with all positive terms. The questions with absolute versus conditional convergence come up more when you have series with positive and negative terms. So, theorem, if a series converges, then it converges absolutely. And let's see if we can get a justification for this. Okay, so first let's try to get a less formal, more visual reasoning for this. So we've got a series. First off, if your series has all positive terms, and we've mentioned this before, but let's look at it again. So we've got a series with all positive terms and all bigger than 0. what does it look like visually when I add up these things? Well, of course, I start with A1, right? I'm going to add A1, and that's positive. That's going this way. And then I add A2 to that, and I get the next partial sum, which is A1 plus A2. So this is A1, this is A2. Of course, A1 is equal to S1. And then I add again to that, and I get S3. The thing is my partial sums just get bigger and bigger, right? And it could be that this thing just gets bigger and bigger and bigger, goes off to infinity, or it could be that these things go to zero so quickly that in fact it goes to some limit here, which we call S. It depends on how quickly those terms are going to zero. Now, if you've got a series that is not alternating, the thing is you might undo things here. I mean, if you've got a series that's not all positive, you end up kind of going backwards sometimes, right? And you're undoing things, which if terms are going to zero, things are going to close in on each other, but you're making it more likely that you're going to converge into something. If the terms are going to zero, things are closing into each other, but you're not as likely to go off to infinity. Okay, so the thing is if visually speaking, if the terms are all positive, you're just getting bigger and bigger and bigger as you're adding. Whereas if you have some negative terms, if the terms are still going to zero, they're still going to close in on each other. They're going to get closer and closer together in each step, but they're not as likely to go off to infinity, so there's more of a chance of convergence. So that's kind of a visual way of thinking about why absolute convergence implies implies convergence. Why, if the absolute values of the terms converge, then it converges conditionally as well. And let's go through another quick, sort of more formal proof. So we're going to assume that the series AN converges absolutely. So that means that this thing here converges, right? The sum of the absolute value, this converges. So we know that AN is either equal to the absolute value of AN or equal to the negative of the absolute value of AN, but more to the point, that means that this 0 is less than or equal to AN plus the absolute value of AN, which is less than or equal to 2 times the absolute value of AN. So if AN is equal to AN, this sum is equal to 2 times the absolute value of AN. If AN is equal to the negative of that, this sum is equal to 0. So it's one of those two endpoints. In particular, it's in between those. So we know that 2 times absolute value AN converges, right? So by the comparison test, that tells us AN plus absolute value AN converges. But since I can add and subtract converging sequences to get converging sequences, that tells us that this thing here minus this series here, which can be rewritten as this here, AN plus absolute value AN minus absolute value AN, which of course can be written as what? Yeah, the sum of AN. This also converges. So since we know both this and this converge, their difference also converges. And that's a good place to stop. End of proof. Okay, on to the next one. Bye.